Alright, boys. Welcome to another LeetCode video. And this time it's weekly contest 375. Okay, so yeah, I'm gonna try to solve problems fast. Okay, load please. That's the first step to winning contest, by the way, is to actually see the problem. What in the frick is this? Hold on. Um, so we want the last digits? Okay, hold on. So each thing can be this thousand. I could cheese this. Can I? Does it work? I think so. Let me go to my template. I think I just simply do power mod. At least that's what I think. So, I just take 10? That's so weird. And then I do power mod again. So X it's Okay. Um, I have no idea if this works, by the way. Does it actually? Oh, yeah. I want to access it like this. Okay. Y is equal to C. Okay. I think it's just modulo. It should be fine. Like it doesn't have to be for prime, like where you modulo 1,000,000,007, right? Because this is just that. Okay. Crap. Okay. What could I do? The maximum element of nums. Okay. Oh, I thought it's like the maximum element of that subarray appears k times. That would have made it a little bit harder, but they did it that way. I guess I'll just do. Let's say the first true, I guess. So we'll say I and n minus 1 p of I plus. So p of n plus 1 minus p of I is really equal to k. I think that works. Let me just make sure I'm not being drunk. Should be fine. Just gonna declare variables first. Partition into one or more, so it's split into continuous subarrays. No two. Okay. Yeah, so if so we I think it's just combinatoric, so I might need factorial. Okay, so we keep track of the hmm. Hold on, let me think for a second. So I know if the subway wants to grab a number, it has to grab every recurrence of that number. Now the kind of troubling part is that it can either grab that number on its own or it can leave it with some other subarray. Hence the partitioning. So I can easily do O n squared dp. It's like a prefix sum dp to avoid timeout. Okay, first of all, So grab something like this. And that becomes, we need to grab these things total. So now we can either leave it like this or we can grab like this. I need, so just have to find the, so well, so now I have it set up. How do I compute this dp? Because the answer is not just the power of the maximum number of distinct groups. I swear there is a math thing about the number of partitions, but I do not know that. So what is this? So it starts with 1, right? And then 2 came through 2, 1. So it's like dp plus equal to Something like that. I have no freaking idea. The answer will actually start at 0. So 1, so this has a 1. 4, 1, 2. Good. At least we're getting a number of groups right. So 1, what is the math thing? Oh, I think it's just, I, I think I know the math. I think I know the math. Got 'em, bro. Easy peasy. I found an intuitive way. So, return how mod 2k minus 1 m voila. Yeah, and GG. So, I'll explain my code now. So, for the Q1, you basically just deal with the question asked. You check if the current element is greater than 0, then you can minus all the devices after it by 1 while keeping it at 0. So what I did was I did brute force, but you can actually do this in linear time by keeping track of how much you decrease by far, and that way So something like this. So this is the amount you decrease so far. It's like a minus k. That's like k plus plus. Crap, I forgot a semicolon. Yeah, so it gives the same result. And if I were to run this, then, it's also accepted. So that's Q1. Q2 is double modular exponentiation. So this is a very, very, very common algorithm you'll use, especially in competitive programming. So it's good to at least have it as something you can copy paste. Because I'm also just literally doing the question asked. So I took the first element in the variable to a power second element variable, and I supplied the mod. Now initially I had some thought about, whether would this work because it's a prime, or I don't know what I was thinking, but it's just modulo m. Like, it doesn't need to be a prime. The prime is just because a lot of times you have to keep your answer small. So they ask you to modulo 1,000,000,007. But you can do this with any mod. So yeah, this is the result of this inner operation. And then take the result of this, and I take it to power of ci, which happens here. And I just check if it's equal to target. So it's not bad at all. You just have to know the binary exponentiation. And don't feel guilty if you don't know how this works. Like, I thought about it quite a bit in order to intuitively understand what it's doing and how it runs so fast, but yeah, just have it as a copy paste. So this one, what I did was I did binary search on the boundary on where. Okay, so first of all, let me establish something. I'm doing kind of like brute force check in the sense that I'm checking. So I start at every single index. That's the start of my subarray. And that way I won't miss anything. So now I just binary search on the right boundary for subarray such that it is the first index where it has the amount of maximum element I need. And in order to compute that information, we can use the help of prefix sum. This L variable is bad, but basically this should have been R. So this will A of L to R is going to be the shortest subarray starting at I that has at least k max elements. And then we also know that if we expand this subarray to the right, it's always going to keep that amount. It's just that we need at least this subarray. So we can keep expanding this till the end, and then we can just count how many subarrays we have with this. And then for the last problem, I found a really, really good intuition on how to calculate the answer. But first, there is something you have to do, which is determine the maximum amount of distinct subarrays you can have. So in this case, every single element can be in their own subarray. But when you have something like this, if you take a 1, well, you have to take all the 1s because you cannot give any other 1s to any other subarrays because of this condition. So, and the thing is, like, if you have like 1x, 1x, 3, 1, 2, 3. So while you're looking at the 1, right, you know, in order to take all the 1s, you need to take this much. But then when you have a 3, you also need to expand further to take this 3. So in reality, this entire thing we have to take all at once. Because this 1 and 3 being interleaving. So here k is the maximum number of subarrays we can separate it into. So see, this map stores like the farthest index for any given element. And we guarantee don't really run to each different element once because like we're trying to expand our subarray to see how much we need. So we start with a single element and then like if this element is further than we expected, then we update this far variable. This far is going to be our right boundary. So it's like I bar. So that is going to be our subarray at the end. And that is the shortest subarray, by the way. And then just implement k. Now, in order to explain this, so I realized, let's say you have groups of subarrays like this, right? These are all smallest as possible. So k is equal to 5. So I had this really cool idea. Honestly, I'm proud of coming up with it. Is I have another visualization. So let's say if I were to, take these two together, right? Combine them to make a one group. Then I imagine this little chain in between them, linking these two, literally. So if I want to include all three of these, then I just link them together. So you can see I have a chain in between the groups. So how many slots of chains do I have? So these are the places where I put my chains. So this is going to be k minus 1 chain. Now we can like chain here, here, and here, or we can just like do this configuration, or we can do this. So in order to get all the possibilities, this is just 2 to the power of k minus 1. Why? Because remember, every single spot, you have two choices. You can either have a chain there or not. So, two choices. So, and then every single thing has two choices. So 2 multiplied k minus 1 times is 2 to the power k minus 1. So yeah, I thought that was interesting. But I remember there is a specific math thing for number of partitions. So like number of partitions of a set. I don't know, I might be misremembering. Okay, I don't know what the heck this is. But okay, so yeah. 2 to the power of k minus 1. But first you have to find the k, which is not that bad to do. And then you don't need to use power mod, since k is like constrained to n, which is the length of input. You can just multiply the twos natively. It's not like you have to do this multiple times. Then you probably want to have a power mod. But yeah, see you boys.